Before jet fighters existed, aircraft were powered by propellers. These planes performed well during World War II, but by the late 1940s they were reaching their limits. Engineers could only push propeller engines so far before they became unstable, inefficient, and unsafe at higher speeds. Pilots also began to notice something strange. As aircraft flew faster, the air around them behaved differently. Controls felt heavier, wings reacted in unexpected ways, and at certain speeds planes began to shake or feel difficult to control. It became clear that aviation was approaching a major turning point. Jet engines offered a new solution. Instead of pulling air with spinning blades, they pushed air backward at high speed, allowing aircraft to fly faster, climb higher, and operate in thinner air. The United States understood that mastering jet flight would shape the future of aviation, even though early jet technology was still new, risky, and not fully understood. This moment marked the beginning of the first American jet fighters. At first, building jet fighters was not about perfection, it was about learning. Early jet aircraft behaved very differently from propeller planes. They accelerated faster, climbed quicker, and reacted more sharply to control inputs. Pilots had to change the way they flew, and engineers had to rethink almost everything they thought they knew about aircraft design. One of the most important lessons was the need for new wing shapes. Straight wings, which worked well on propeller aircraft, created too much drag at high speed. To solve this, designers began using swept wings, angled backward to help air flow more smoothly as speed increased. This idea would soon prove essential. The aircraft that truly helped the United States understand jet flight was the F-86 Saber. It was designed with swept wings, which gave it better stability and control at high speed, and it featured a carefully planned cockpit that helped pilots stay aware of their surroundings while flying much faster than before. What made the F-86 special was not just its performance, but how forgiving it was to fly. Pilots could make mistakes and recover, which was extremely important during this early learning stage of jet aviation. Engineers closely studied how the Sabre behaved in the air, learning how jets turned, how they lost speed, and how they reacted when pushed near their limits. These lessons were later written into manuals, training programs, and future aircraft designs. And for the first time, the United States felt confident that it truly understood how jet fighters should be built and flown. With this new confidence, designers decided to push jet technology even further. The result was the F-100 Super Saber, an aircraft built to fly beyond the speed of sound in level flight. This achievement marked a major milestone, but it also brought new challenges. At these speeds, the aircraft experienced extreme stress, airflow became unpredictable, and even small design flaws caused serious control problems. Pilots found the F-100 difficult to handle at times, especially during takeoff and landing. Instead of ignoring these issues, engineers carefully studied them, improving the aircraft's stability, refining its controls, and learning how airflow behaves near and beyond the speed of sound. The F-100 taught a crucial lesson. Speed alone was not enough, and future jet fighters needed balance, stability, and strong attention to pilot safety. By the end of the 1950s, the United States had learned how to build jet aircraft that were both fast and stable. Engineers now understood swept wings, jet engines, and high-speed flight much better than before. But aviation was not standing still. As the world moved into the 1960s, aircraft began flying higher and faster, and the sky became filled with new technology. Pilots could no longer depend only on what they could see with their own eyes. Designers started asking new questions. How could pilots see farther than human vision allowed? How could aircraft detect other planes in clouds or darkness? And how could machines help pilots make decisions more quickly? These questions marked the beginning of a new era, where fighter jets were no longer just fast airplanes. To solve these new problems, engineers turned to technology that could help pilots see beyond human vision. This technology was radar. Radar allowed aircraft to detect objects far away, even in clouds or darkness, and gave pilots more time to understand what was happening around them. Instead of reacting at the last moment, pilots could now plan ahead. This change marked a major shift in aviation. Fighter jets were no longer designed only around speed and aerodynamics, but around information and awareness. Adding radar to fighter jets changed far more than just what pilots could see. Radar systems were large, heavy, and required significant electrical power. To carry this new technology, aircraft needed bigger noses, stronger structures, and more complex internal systems. This caused fighter jets to grow in size and weight. Cockpits also changed. Pilots now had to read screens and instruments, not just look outside the aircraft. Managing information became just as important as flying itself. As radar and electronics became more advanced, pilots faced a new challenge. Flying the aircraft while managing complex systems at the same time was demanding. Engineers realized there were limits to how much information one person could handle. To reduce workload, some aircraft were designed with two crew members. One focused on flying, while the other managed radar and systems. This decision reflected a growing understanding that technology should support the pilot, not overwhelm them. One of the first American fighter jets designed around radar, electronics, and multi-crew operation was the F-4 Phantom II. When the Phantom entered service in the early 1960s, it immediately stood out from earlier jet fighters. It was larger, heavier, and more powerful, but these traits were not accidental. The aircraft was built this way to support a completely new approach to flying. Earlier fighter jets were designed mainly around speed, maneuverability, and pilot skill. The Phantom was different. It was designed around information. Its shape, size, and internal layout reflected the growing importance of radar, sensors, and coordination between humans and machines. The Phantom was built to carry large radar equipment in its nose, along with extensive wiring, cooling systems, and electronic components spread throughout the aircraft. This required more internal space and a stronger structure. As a result, the aircraft grew in size compared to fighters from the 1950s. This was a major shift in design thinking. Engineers were no longer trying to make the smallest or lightest possible aircraft. Instead, they focused on creating a platform that could manage complex systems reliably over long periods of flight. The Phantom became one of the first fighter jets where the systems were just as important as the airframe itself. Inside the cockpit, the Phantom reflected another important change. It used a two-crew layout. The pilot sat in the front seat, focused on flying the aircraft. Behind the pilot sat a second crew member, responsible for managing radar, navigation, and other onboard systems. This arrangement was not about comfort. It was about human limits. By the 1960s, flying a fighter jet meant more than controlling speed and altitude. Pilots had to monitor radar displays, manage communications, track information, and make decisions quickly. Engineers recognized that asking one person to do everything was no longer realistic. The two-crew cockpit of the F-4 showed a growing understanding that aviation was becoming a team effort, even inside a single aircraft. Flying the Phantom felt very different from earlier jets. The cockpit was filled with instruments, screens, switches, and indicators. Pilots and crew members spent much of their time looking inside the aircraft, interpreting information, and coordinating with each other. This changed training completely. Pilots now had to learn how to work with systems, not just fly by feel. Crew coordination became a skill of its own. Communication, timing, and trust between the two crew members were essential for smooth operation. The Phantom helped redefine what it meant to be a fighter pilot in the modern era. Because the F-4 carried so much equipment, it needed powerful engines to move its weight. This gave the aircraft impressive performance, but it also introduced trade-offs. The Phantom was not as light or agile as some earlier fighters. Instead, it relied on awareness, planning, and system support. This was a clear sign that fighter design priorities had shifted. Engineers accepted these trade-offs because the benefits were greater. The Phantom could operate in more conditions, process more information, and support its crew in ways older aircraft could not. The F-4 Phantom became a learning platform for an entire generation of aircraft designers. Engineers studied it closely and learned how to integrate radar and electronics into a fighter jet, how cockpit layout affects pilot workload, and how crew coordination improves safety and efficiency. They also saw how complex systems change training requirements and maintenance needs. Not every idea worked perfectly, and some designs revealed new challenges, but every lesson helped move aviation forward. The Phantom proved that fighter jets had entered a new era, where information and teamwork mattered just as much as speed. The influence of the F-4 extended far beyond its own service life. The aircraft proved that complex, system-driven fighters were possible and practical. It paved the way for future designs that would refine these ideas even further. Later jets would become more efficient, more automated, and easier to manage. But many of their core concepts, radar integration, crew workload management, and systems-focused design, were proven during the Phantom era. By the late 1960s and the early 1970s, the lessons of the F-4 Phantom were becoming clear. Fighter jets were now extremely powerful and highly capable, but they had also grown larger, heavier, and more complex. This forced designers to stop and think. Could aircraft be made smarter without becoming too heavy? Could complexity be reduced without losing capability? And where were the real limits of this systems-heavy approach? The search for answers to these questions would shape the next generation of fighter jets. One response to the growing complexity of fighter jets in the 1960s was to push existing ideas even further. If radar, electronics, and speed had improved performance, some designers believed the answer was to build larger aircraft with more power and greater range. This thinking led to the creation of the F-105 Thunderchief. At first glance, the F-105 looked extreme. It was one of the largest single-engine fighter jets ever built. Its long fuselage, massive air intake, and powerful engine reflected a design philosophy focused on raw performance. The Thunderchief was built to move fast, carry heavy loads, and operate over long distances. But this size and power came with important consequences. The heart of the F-105 was its engine. To achieve the speed and range designers wanted, the aircraft needed enormous thrust. This required a large engine, which in turn demanded a bigger airframe to support it. As a result, the Thunderchief grew much larger than earlier fighters. Its structure had to be stronger. Its systems had to be more robust. Everything about the aircraft reflected the challenge of controlling so much power in a single design. This made the F-105 impressive on paper, but difficult in practice. As aircraft grew larger, complexity increased across every part of the design. The F-105 carried advanced systems, navigation equipment, and electronic components that added weight and required careful management. Pilots flying the Thunderchief had to monitor many systems at once. The cockpit was dense with instruments, gauges, and controls. While radar and electronics provided more capability, they also increased workload. This pushed pilots closer to their limits. Flying the aircraft required constant attention, precise control, and careful planning. Small mistakes could quickly become serious problems. The Thunderchief also revealed how complexity affects maintenance. Large engines, dense wiring, and tightly packed systems made repairs more difficult and time-consuming. Engineers learned that building more powerful aircraft also meant creating machines that were harder to maintain. Every additional system added weight, heat, and stress to the airframe. This raised an important question for designers. Was it sustainable to keep building bigger and more complex fighter jets? The F-105 taught designers a crucial lesson. Power alone was not enough. Speed alone was not enough. Even advanced systems could become a problem if they overwhelmed pilots and maintenance crews. The Thunderchief showed that fighter jet design had real limits. Beyond a certain point, increasing size and complexity reduced flexibility rather than improving it. This realization forced engineers to rethink their approach. By the late 1960s, it was clear that the path represented by the F-105 could not continue indefinitely. Fighter jets needed a better balance between capability, workload, and reliability. Designers began to shift their focus. Instead of pushing raw power further, they started asking new questions. How can pilots understand their environment earlier? How can information reduce the need for extreme speed? How can aircraft help crews plan instead of react? These questions marked another turning point. The F-105 did not fail as an aircraft. Instead, it succeeded as a teacher. It showed designers where the limits of size, speed, and complexity truly were. From the Thunderchief, engineers learned that future fighter jets needed to be smarter, not just stronger. Awareness, planning, and coordination would matter more than pushing performance to extremes. This shift in thinking would lead directly to the next major aircraft of the era. One designed not just to move fast, but to see far ahead and manage information effectively. The answer to the challenges revealed by the F-105 was not more power, it was better awareness. And that idea would shape one of the most recognizable fighter jets ever built. That aircraft was the F-14 Tomcat. From the beginning, the F-14 was designed around awareness. Rather than focusing only on raw speed or engine power, engineers focused on how far the aircraft could see, how much information it could manage, and how well its crew could plan ahead. The Tomcat was built to detect and track multiple objects at long distances. This allowed pilots and crew members to understand what was happening far beyond their immediate surroundings. This was a major shift. The goal was no longer just to react quickly, but to anticipate events before they happen. One of the most noticeable features of the F-14 was its variable sweep wings. These wings could change position during flight, moving forward at lower speeds and sweeping back at higher speeds. This design allowed the aircraft to remain stable and efficient across a wide range of conditions. It could take off and land safely, fly efficiently at long distances, and still perform well at higher speeds. The variable wings reflected the Tomcat's overall philosophy. Adaptability mattered more than pushing one extreme. Like the F-4, the F-14 used a two-crew cockpit. The pilot in the front seat focused on flying the aircraft. The second crew member in the rear seat focused on managing radar, tracking information, and interpreting data. This division of responsibility allowed each person to focus on their strengths. Instead of overwhelming a single pilot, the workload was shared. The Tomcat showed how teamwork inside the cockpit could dramatically improve effectiveness and safety. The radar systems on the F-14 were designed to do more than simply detect objects. They were built to help crews build a picture of the environment. The aircraft could track multiple contacts at once, allowing the crew to understand patterns and movement over time. This gave pilots more time to think, decide, and plan. Radar was no longer just a warning tool. It became a core part of decision-making. The F-14 became another important learning platform for engineers. From it, designers learned how long-range awareness reduces pressure on pilots, how shared workload improves decision quality, how flexibility in design improves overall performance, how planning can replace last-second reactions. The Tomcat showed that information, when managed correctly, could reduce the need for extreme speed or size. While the F-14 was still a powerful aircraft, it represented a more balanced approach. Designers were no longer chasing maximum performance at any cost. Instead, they focused on building an aircraft that could operate effectively across many situations without overwhelming its crew. This balance became one of the Tomcat's greatest strengths. But even as the Tomcat proved how powerful balance could be, it also revealed something else. Fighter jets had reached a level of complexity that could not keep growing forever. Designers now faced a difficult question. How far could technology be pushed before it began to work against the pilot? Could future aircraft remain powerful and aware without becoming heavier, more expensive, and harder to manage? The answer would not come from making jets bigger. It would come from rethinking how energy, weight, and the pilot work together. This shift in thinking marked a quiet but important change in aviation. For years, progress had meant adding more systems, more equipment, more complexity. But now designers began to step back. They started asking not what could be added, but what could be removed. Engineers realized that a fighter jet's true performance was not defined by speed alone. It was defined by how well the aircraft could use its energy. Energy was everything. How quickly a jet could climb, how fast it could turn, how efficiently it could trade speed for altitude and altitude for speed. If an aircraft wasted energy, no amount of technology could save it. This idea became known as energy management. It focused on balance between thrust and weight, lift and drag, power and control. Just as important, designers placed the pilot back at the center of the aircraft. Instead of forcing pilots to manage endless systems, the aircraft itself would work with them. Controls would feel natural. Information would be clear. The jet would respond quickly and predictably. This philosophy did not reject technology, it refined it. The goal was simple: build fighter jets that were powerful without being overwhelming. This new approach would soon give rise to a different kind of aircraft, lighter, faster to respond, and built around the pilot. The first clear result of this thinking would be a fighter designed to dominate the sky through raw power. The aircraft that emerged from this new way of thinking was the F-15 Eagle. From the very beginning, the F-15 was designed with a clear priority. It needed to control the sky through power energy, and reliability, not through excessive complexity. Designers wanted an aircraft that could climb faster, accelerate harder, and maneuver without hesitation. To achieve this, they focused on one key idea. The F-15 had to have more power than weight. This concept, known as a high thrust-to-weight ratio, meant the aircraft could accelerate vertically, regain energy quickly, and stay in control even during demanding maneuvers. Instead of struggling to recover speed, the Eagle could simply power its way out. This gave pilots confidence. Unlike some earlier aircraft, the F-15 was not built to overwhelm the pilot with systems. Its cockpit was designed to be clear and logical. Information was presented where it mattered, without unnecessary distraction. Controls felt direct and predictable. The aircraft responded quickly to pilot input, making it feel less like a machine that needed to be managed and more like an extension of the pilot's intent. This was not an accident. Designers believed that an aircraft should work with the pilot, not against them. The F-15 reflected this belief in every part of its design. The Eagle's large engines gave it exceptional performance. It could climb rapidly, reach high altitudes, and maintain energy during turns better than many aircraft of its time. But power alone was not the goal. What mattered was how that power was used. The F-15's wings and airframe were designed to support high maneuverability without sacrificing stability. Even at high speeds, the aircraft remained predictable and controllable. This balance allowed pilots to focus on positioning and decision-making rather than fighting the aircraft itself. While the F-15 carried advanced systems, its designers avoided unnecessary complexity. They understood the lessons of earlier jets. More systems did not always mean better performance. Every addition had to justify its weight, maintenance cost, and impact on pilot workload. As a result, the F-15 became known for its reliability and effectiveness. It was powerful, but not fragile. Advanced, but not overloaded. This made it easier to maintain, easier to train on, and easier to trust. The F-15 proved that balance did not mean compromise. It showed that an aircraft could be extremely powerful while remaining manageable, that advanced technology could support the pilot instead of replacing them, and that simplicity, when combined with strength, could be a decisive advantage. Designers learned that the best fighter jets were not those that tried to do everything at once. They were the ones that did the most important things exceptionally well. The success of the F-15 confirmed that the shift away from excessive complexity was the right decision. But designers were not finished. They began to ask another question. If these ideas worked for a large, powerful aircraft, could they also work for a lighter, more agile fighter? Could a jet be designed almost entirely around the pilot's instincts? The answer would come in the form of a very different aircraft, one that changed how pilots and machines interacted forever. That aircraft was the F-16 Fighting Falcon. The F-16 was never meant to be large or heavy. It was meant to be light, agile, and responsive. Designers believed that a smaller aircraft, if built correctly, could react faster, turn tighter, and maintain energy more efficiently than larger jets. But to make this work, the pilot needed complete confidence in the aircraft. That meant changing how pilots interacted with their jets. One of the most important changes in the F-16 was the removal of traditional mechanical controls. Instead of cables and linkages directly moving the aircraft's surfaces, the F-16 used a system called fly-by-wire. When the pilot moved the controls, computers translated those movements into precise commands. These computers constantly adjusted the aircraft to keep it stable and efficient. This allowed the F-16 to fly in ways that would be impossible for older aircraft. It could remain stable even when pushed to its limits. At first, trusting computers with control was uncomfortable. But over time, pilots realized something important. The aircraft was not taking control away. It was protecting them. Everything about the F-16 cockpit was designed to reduce effort and improve awareness. The pilot sat in a reclined seat, reducing strain during high-speed turns. Controls were placed where the pilot's hands naturally rested. Information was displayed clearly, without clutter. Even the side-mounted control stick was designed to reduce unnecessary movement. Small inputs produced smooth, precise responses. The goal was simple. The pilot should think, and the aircraft should respond. The F-16's lightweight allowed it to use energy extremely well. It could accelerate quickly, change direction rapidly, and maintain control without wasting power. Instead of relying on size or complexity, the aircraft relied on efficiency. Pilots often describe the F-16 as feeling alive, responsive, predictable, forgiving. It did not fight the pilot. It worked with them. While the F-16 included advanced systems, they were designed to support the pilot quietly. Radar, navigation, and flight control systems worked in the background, allowing pilots to focus on flying and decision-making. This approach reflected a major shift in design philosophy. Technology no longer demanded attention. It served the pilot instead. The F-16 proved that fighter jets did not need to be large to be effective. They did not need endless systems to be capable. What mattered most was balance. Balance between pilot and machine. Balance between power and weight. Balance between technology and instinct. Designers now understood that the best aircraft were those that amplified human ability rather than replacing it. The success of the F-16 reshaped fighter design around the world. Its philosophy influenced future aircraft for decades. It showed that simplicity, when done correctly, could be just as powerful as complexity. And it confirmed something pilots had always known. The human element still mattered. By the late 1970s and early 1980s, fighter jet design had reached a new balance. Aircraft were powerful, aware, and responsive, without being overwhelming. The lessons of the F-15 and F-16 would guide everything that followed. But aviation was not finished evolving. The next challenge would be stealth, in a future where aircraft were designed not just to fly fast, but to remain unseen. By the time the F-16 entered service, fighter jet design had reached an important moment. Aircraft were powerful, they were agile, they were efficient, and they were built around the pilot. For the first time, designers felt they had achieved balance. But even as this balance was reached, a quiet problem continued to grow in the background. No matter how fast or maneuverable a fighter jet was, it could still be detected. Radar systems had not stood still. They had become more sensitive, more accurate, and more widespread. Air defenses could now track aircraft from farther away. They could follow fast targets. They could see through clouds, darkness, and weather. This meant something important. A fighter jet no longer needed to be seen with the human eye to be tracked. It could be detected long before it ever reached visual range. For decades, fighter jets had evolved in a predictable way. If radar improved, aircraft flew faster. If threats increased, jets climbed higher. If enemies reacted quicker, pilots maneuvered harder. But by the late 1970s, designers began to realize something uncomfortable. There were limits to this approach. Aircraft could only become so fast. Pilots could only endure so much strain, and maneuvering alone could not solve the problem of detection. No matter how well a pilot flew, radar could still see them coming. This led engineers to ask a question that had never been asked so seriously before. What if the problem was not how to fight, but how to avoid being detected in the first place? This idea was radical. It meant stepping away from traditional thinking. It meant rethinking the purpose of speed, power, and even shape. Instead of asking how to outrun radar, designers asked how to avoid radar entirely. Stealth was never about becoming invisible. It was about control. Control over how radar waves interacted with an aircraft. Control over how heat was released. Control over how sensors interpreted signals. Radar works by sending energy outward and listening for reflections. If that energy comes straight back, the object is easy to detect. But if the energy is scattered away, the object becomes much harder to see. Engineers discovered that shape mattered as much as speed. Flat surfaces, sharp edges, angled panels. These shapes could redirect radar energy away from its source instead of reflecting it back. This was completely different from traditional aircraft design, which favored smooth curves and flowing lines for aerodynamic efficiency. Stealth required a new balance. Aerodynamics still mattered, but radar mattered just as much. Stealth did not come without cost. Early stealth designs were not fast, they were not highly maneuverable, they did not look elegant, but they had something no other aircraft had. They could move through defended airspace with far less detection. This changed the rules completely. An aircraft that was not detected did not need to fight its way through threats. It could choose its path, its timing, and its position. At first, many engineers were skeptical. Stealth required trusting calculations over experience. It required building aircraft that looked wrong by traditional standards. It required accepting that some performance would be sacrificed. But the potential advantage was enormous. If stealth worked, everything else would follow. The first aircraft to fully embrace this new philosophy was unlike anything the world had seen. It did not look fast. It did not look graceful. It did not resemble traditional fighter jets at all. Its surfaces were flat and angular. Its shape was dictated by mathematics, not aesthetics. That aircraft was the F-117 Nighthawk. The F-117 was not built to dominate the sky through speed or agility. It was built to avoid detection, and it worked. Radar systems that easily tracked other aircraft struggled to detect it. The aircraft could move where others could not. For the first time, stealth was no longer a theory. It was real. The success of the F-117 proved something critical. Stealth was not a specialty feature. It was a design philosophy. From that moment on, every future fighter jet would need to consider visibility, not just performance. Designers now faced a new challenge. Could stealth be combined with speed? Could low visibility exist alongside maneuverability? Could awareness, power, and stealth coexist in one aircraft? The lessons of the F-117 did not replace earlier ideas. They built on them. Energy management still mattered. Pilot-centered design still mattered. Situational awareness still mattered. But now stealth would sit at the center of everything. The next generation of fighters would not just fly fast. They would manage information. They would control what sensors could see. They would blend performance and invisibility into a single system. This new direction would lead to one of the most ambitious fighter jets ever built, an aircraft designed to combine stealth, speed, agility, and awareness, without overwhelming the pilot. That aircraft would be known as the F-22 Raptor, and it would represent the next major step in the evolution of American fighter jets. When the F-117 Nighthawk first appeared, it did not look like a fighter jet. It did not have smooth curves. It did not have elegant wings. It did not resemble any aircraft that had come before it. At first glance, it looked broken. But this strange appearance was not a mistake. It was the result of a completely new way of thinking. Traditional aircraft were shaped to move smoothly through the air. Their curves reduced drag and improved efficiency. The F-117 ignored those rules. Its shape was built around one goal: reducing radar detection. Instead of smooth curves, it used flat surfaces. Instead of flowing lines, it used sharp angles. Each surface was carefully positioned so radar energy would be scattered away instead of reflected back to its source. One of the most remarkable things about the F-117 is when it was designed. This was before modern computing power, before advanced simulations, before digital design tools. Engineers relied on mathematics, theory, and limited computer models to predict how radar waves would behave. They could not test every idea easily. They had to trust calculations. This made the project risky, but the math was sound. Unlike earlier fighters, the F-117 was not designed around maneuverability or speed. It was designed around physics. Every angle mattered. Every edge mattered. Even small changes could dramatically affect radar visibility. This meant the aircraft's shape was locked in early. Pilots would have to adapt to the aircraft, not the other way around. This was a major shift in aviation thinking. The F-117 had another unusual characteristic. It was naturally unstable. Its shape made it difficult to fly using traditional controls. Left alone, it would not remain steady. This would have made the aircraft impossible to fly, if not for computers. To keep the F-117 stable, engineers relied on a fly-by-wire control system. Computers constantly adjusted the aircraft's control surfaces. They made thousands of corrections every second. The pilot did not directly control the aircraft. Instead, the pilot gave commands, and the computers translated them into safe movements. Without computers, the F-117 could not exist. This marked a major moment in aviation history. For the first time, a combat aircraft depended entirely on computers to stay in the air. Inside the cockpit, the F-117 was quiet and controlled. The pilot did not rely on speed or maneuvering. They relied on planning, precision, and timing. Navigation systems guided the aircraft along carefully planned routes. The pilot followed those paths closely, trusting the aircraft's low visibility. Flying the F-117 required discipline. It was not about reacting quickly. It was about avoiding reaction entirely. The aircraft's nickname, Nighthawk, was not just for style. Early stealth designs were most effective in darkness. Flying at night reduced visual detection. It complemented the aircraft's radar-focused stealth design. This further emphasized that the F-117 was not a traditional fighter. It was a precision tool. Stealth was fragile. The aircraft's surface materials required careful maintenance. Even small imperfections could increase radar visibility. Panels had to be aligned precisely. Coatings had to be maintained carefully. This made the F-117 demanding on the ground, but the benefits were worth the effort. For years, the F-117 remained secret. When it was finally revealed, many people were skeptical. The shape looked impractical. The performance numbers seemed unimpressive. But once the aircraft was used operationally, doubts faded. Radar systems that easily tracked other aircraft struggled to detect it. Stealth was no longer theoretical. It worked. The success of the F-117 sent a clear message to designers around the world. Stealth was not optional. It was the future. Every new fighter design would now need to consider radar visibility from the very beginning. You could not add stealth later. It had to be built into the aircraft's shape, structure, and systems. Despite its success, the F-117 also revealed important limitations. It was specialized. It lacked flexibility. It could not replace traditional fighters. Designers now faced a new challenge. Could stealth be combined with speed, with agility, with air superiority? The F-117 proved stealth could work, but it was only the first step. A bridge to the future. The true legacy of the F-117 was not what it did, but what it made possible. It gave engineers confidence to push further. If stealth could work in a limited aircraft, could it work in a fully capable fighter? One that could fly fast, turn hard, gather information, and remain difficult to detect. That question would lead to the next great leap in aviation. The next aircraft would not be a compromise. It would combine stealth with speed, stealth with agility, stealth with awareness. It would be designed to dominate the sky without being seen. That aircraft was the F-22 Raptor. The F-22 was not designed to replace earlier aircraft. It was designed to redefine what a fighter could be. Instead of excelling in one area, the F-22 aimed to balance many: stealth, speed, agility, awareness, pilot control. This was not about compromise, it was about integration. Everything had to work together from the start. Unlike earlier stealth aircraft, the F-22 did not look sharp or broken. Its stealth came from carefully blended shapes. Edges were aligned, surfaces flowed smoothly. Curves were designed to control radar reflection without destroying aerodynamics. This allowed the aircraft to remain stealthy from multiple angles, not just one direction. Stealth was no longer fragile. It was structural. One of the most remarkable abilities of the F-22 is supercruise. This means the aircraft can fly faster than the speed of sound without using afterburners. Earlier fighters needed afterburners for supersonic flight, which consumed fuel quickly and produced large heat signatures. The F-22 did not. Its engines were powerful enough to maintain high speed efficiently. This gave the aircraft greater range, flexibility, and endurance, all while remaining harder to detect. Speed alone was not enough. The F-22 was also designed to be extremely agile. Its engines used thrust vectoring nozzles, which could move to redirect engine thrust. Instead of relying only on wings and control surfaces, the aircraft could use engine power to help maneuver. This allowed the F-22 to maintain control even at very high angles and low speeds. Agility was no longer limited by airflow alone. While earlier jets added sensors over time, the F-22 was designed around them. Radar, navigation, electronic systems, and communication tools were fully integrated. Instead of showing raw data, the aircraft fused information into a clear picture. The pilot did not need to interpret multiple sources. The aircraft did that work in the background. This reduced workload and improved decision-making. The F-22 was not just fast or stealthy, it was aware. Despite its advanced systems, the F-22 was built around the pilot. Controls were intuitive. Displays were clean and uncluttered. Information appeared only when needed. The aircraft worked silently in the background, supporting the pilot instead of demanding attention. This reflected a lesson learned over decades. Technology should extend human ability, not compete with it. Earlier stealth aircraft had accepted trade-offs. The F-22 refused to. It did not give up speed. It did not give up agility. It did not give up awareness. Instead, it combined all three. This made the F-22 fundamentally different. It could enter airspace quietly, position itself advantageously, and remain difficult to detect throughout flight. The F-22's advanced design came with challenges. Stealth materials required care. Systems were complex. Maintenance demanded precision. But unlike earlier stealth aircraft, these requirements were built into long-term planning. The F-22 was not experimental. It was operational from the start. The F-22 was more than an aircraft. It was the result of everything learned before it. From the F-86 and F-100 came lessons about speed and stability. From the F-4 came systems and crew coordination. From the F-14 came awareness and balance. From the F-15 came power and reliability. From the F-16 came pilot-centered design. From the F-117 came stealth. The F-22 brought it all together. With the F-22, fighter design entered a new era. Aircraft were no longer judged by a single feature. They were judged by how well everything worked together. Speed mattered, but only if it supported awareness. Agility mattered, but only if it preserved control. Stealth mattered, but only if it could coexist with performance. The F-22 set that standard. The F-22 represents the peak of one philosophy, a philosophy built around dominance through integration. But aviation never stops evolving. As technology continued to advance, designers began exploring a new idea. What if multiple aircraft could work together as a system? What if sensors, data, and networks mattered more than individual performance? That thinking would shape the next chapter. The next evolution would focus on connectivity, shared awareness, and aircraft designed to operate as part of a larger network. That future would take form in the F-35 and beyond. The F-35 was not designed to be another F-22. Instead of focusing on extreme performance in every category, it was designed around integration. The goal was not to build the fastest or most agile fighter ever. The goal was to build an aircraft that could see everything, understand everything, and share that understanding with others. The F-35 was meant to operate as part of a system, not as a standalone machine. Like the F-22, the F-35 was designed with stealth built into its shape. Its surfaces were carefully aligned. Edges were shaped to reduce radar reflection. Materials were chosen to minimize visibility across multiple sensor types. But the F-35 took a slightly different approach. Instead of maximizing stealth at all costs, designers balanced stealth with versatility and affordability. The aircraft was intended to be used widely across different environments and missions. Stealth was not the final goal, it was the starting point. The defining feature of the F-35 is not its speed or its shape, it is its sensors. The aircraft is covered in systems designed to gather information. Radar scans the airspace. Infrared sensors watch for heat signatures. Cameras provide full spherical awareness around the aircraft. The F-35 does not just look forward, it looks everywhere. This allows the aircraft to build a complete picture of its surroundings in real time. What truly sets the F-35 apart is how it handles information. Instead of presenting raw data from each sensor, the aircraft combines everything into a single unified picture. This is called sensor fusion. The pilot does not need to interpret multiple screens. The aircraft processes the data first, then presents clear, meaningful information. Threats are identified, locations are prioritized, important details are highlighted. The result is clarity. The pilot spends less time managing systems and more time making decisions. One of the most visible symbols of the F-35's philosophy is its helmet. Instead of relying on traditional cockpit displays alone, the pilot's helmet projects information directly onto the visor. Flight data, sensor images, and targeting information move with the pilot's head. In some situations, the pilot can even see through the aircraft, using cameras that project a live view of what lies below or behind. This eliminates blind spots. The cockpit no longer ends at the canopy. It extends into the airspace around the aircraft. The F-35 was designed from the beginning to share information. Data gathered by one aircraft can be transmitted to others. This includes other fighters, ground systems, ships, and command centers. One F-35 can act as a forward sensor, Another can act on the information. Others can support from different positions. This turns a group of aircraft into a coordinated network. The strength of the system does not depend on a single jet. It depends on connection. The F-35 exists in multiple versions, designed for different environments. One operates from conventional runways. Another is designed for short takeoff and vertical landing. Another is optimized for carrier operations. Despite these differences, the core philosophy remains the same: shared awareness, integrated systems, pilot-centered design. The aircraft adapts to its role without abandoning its identity. The F-35 is often compared to earlier fighters based on speed or maneuverability, but that comparison misses the point. The F-35 does not rely on reacting faster. It relies on knowing earlier. By detecting threats sooner, sharing that information instantly, and positioning itself intelligently, the aircraft reduces the need for extreme maneuvers. Performance comes from understanding. In earlier generations, pilots were primarily flyers. Then they became system managers. Then they became information managers. With the F-35, the pilot becomes something else: a decision maker. The aircraft handles sensing, filtering, and prioritizing. The pilot focuses on intent, timing, and coordination. This represents the latest evolution in human-machine partnership. The aircraft does not replace the pilot. It amplifies them. The F-35 teaches a different lesson than earlier fighters. It shows that dominance does not come from a single attribute. It comes from integration, from shared awareness, from cooperation, from systems working quietly in the background. The aircraft itself is only one part of a much larger picture. Because the F-35 represents such a different philosophy, it has often been misunderstood. Some expected it to replace every aircraft directly. Others expected it to excel in traditional performance categories. But the F-35 was never meant to be judged by old standards alone. It represents a shift in how air power is used, not as isolated machines, but as connected systems. The F-35 does not mark the end of fighter development. It marks a transition toward aircraft that operate together seamlessly, toward systems that extend across air, land, sea, and space, toward a future where information matters more than individual speed. The fighter jet is no longer just an aircraft. It is a node in a network. With the F-35, the story of American fighter jets reaches a new phase. From propellers to jets, from speed to awareness, from power to balance, from stealth to integration. The next step will go even further. Uncrewed systems, artificial intelligence, aircraft that think alongside humans. The future of air combat is no longer just about flying. It is about connection. By the time the F-35 entered service, fighter jets had changed in ways early designers could never have imagined. They were no longer just aircraft. They were no longer defined by speed alone. They were no longer fighting as individuals. They had become part of something larger, a system. For most of aviation history, progress focused on building better individual machines, faster engines, stronger airframes, more capable pilots. But in the modern era, designers began to realize something important. No single aircraft, no matter how advanced, could dominate the sky alone. The future would belong to teams, not individuals. Future fighter jets are being designed to operate as part of a network. Instead of each aircraft seeing only what its own sensors detect, information will be shared instantly across many platforms. Fighter jets, drones, ships, ground systems, satellites. Each piece contributes to a shared picture of the sky. This means a pilot may act on information gathered by another aircraft hundreds of miles away. Awareness is no longer local, it is collective. One of the most significant changes ahead is the growing role of uncrewed aircraft. These systems are not designed to replace pilots. They are designed to support them. Uncrewed aircraft can fly ahead. They can observe. They can relay information. They can take risks without placing a human in danger. In the future, a single piloted fighter jet may operate alongside several uncrewed companions, each performing a specific role. The pilot becomes a coordinator, not just a flyer. As aircraft systems become more complex, artificial intelligence will play a larger role. But this does not mean machines will make decisions alone. The goal is assistance, not replacement. AI systems can help manage information, They can highlight threats, they can suggest options, but the human remains responsible for judgment. The future of fighter jets is not about removing pilots. It is about reducing their burden. Earlier generations of fighters were defined by clear metrics: top speed, climb rate, turn performance. Future aircraft will be judged differently. How quickly can they adapt? How well can they integrate with other systems? How easily can they be upgraded as technology evolves? Flexibility will matter more than perfection. Aircraft will be designed to evolve over time rather than remain fixed. Stealth will continue to play a role, but it will change. Instead of relying only on shape and coatings, future aircraft will focus on managing signatures across many domains. Radar, infrared, electronic signals, data transmissions. The goal is not invisibility, it is control. Control over when an aircraft is seen and when it is not. The pilot of the future will not simply fly the aircraft. They will manage information, coordinate assets, make decisions based on a wider picture than ever before. Training will focus less on physical limits and more on cognitive skill. Understanding systems, interpreting information, maintaining situational awareness. The cockpit will become a command space. One of the greatest challenges for future fighter design is uncertainty. Technology changes quickly. Threats evolve. New sensors and systems appear constantly. Designers now accept that they cannot predict everything. Instead of building aircraft for a single threat, they build platforms that can adapt. The future fighter is not a finished product, it is a framework. As sensors improve and engagement ranges increase, close-range encounters may become less central. This does not mean maneuverability no longer matters. It means maneuverability becomes one tool among many. The emphasis shifts from reaction to preparation. Looking back across decades of fighter development, a pattern becomes clear. Each generation did not replace the one before it. It built upon it. Speed mattered, then awareness mattered, then balance mattered, then stealth mattered, then integration mattered. The future will combine all of these ideas, from speed to awareness, from individual action to coordination. Despite all the technology, some things remain constant. Human judgment still matters. Clear thinking still matters. Discipline, training, and decision-making remain central. Fighter jets may become smarter, quieter, and more connected, but they are still tools designed to serve human intent. Human judgment still matters. Clear thinking still matters. Discipline, training, and decision-making remain central. Fighter jets may become smarter, quieter, and more connected, but they are still tools designed to serve human intent. A final reflection from propeller aircraft to jet engines, from simple cockpits to flying systems, from individual machines to connected networks. The story of fighter jets is not just a story of technology, it is a story of how humans learn, adapt, and rethin. For most of aviation history, success depended on the performance of a single aircraft and its pilot. Each jet operated mostly on its own, relying on its own sensors and decisions. That idea is now changing. Future fighter jets are being designed to work together, sharing information instantly. What one aircraft sees, others can see as well. This means awareness is no longer limited to one cockpit. It is shared across the entire force. One of the biggest changes in the future of fighter aviation is the rise of uncrewed systems. These aircraft are not meant to replace pilots. They are meant to support them. Uncrewed aircraft can fly ahead, observe, collect data, and relay information back to piloted jets. They can take risks without putting a human life in danger. In the future, a single fighter jet may operate alongside multiple uncrewed companions, each with a specific role. The pilot becomes a leader and decision maker, not just a flyer. As fighter jets become more complex, computers and artificial intelligence will play a larger role. These systems will help manage large amounts of information. They will highlight important details and reduce unnecessary workload. But they are not meant to replace human judgment. The pilot remains responsible for decisions. Technology exists to assist, not control. The future of fighter jets is about cooperation between humans and machines. Stealth will continue to matter, but it is changing. In the past, stealth focused mainly on aircraft shape and materials. In the future, it will also involve managing electronic signals, heat, and data emissions. The goal is not to be invisible at all times. The goal is to control when and how an aircraft is detected. Stealth becomes flexible, not fixed. Future fighter jets may not always be faster or more agile than earlier aircraft. Instead, they will perform better because they understand the situation earlier. Knowing where threats are, where friendly systems are, and how the environment is changing gives pilots an advantage long before action is required. Performance comes from awareness, not reaction. One lesson designers have learned is that technology changes quickly. Instead of building aircraft that remain the same for decades, future fighters are designed to adapt. New sensors, software updates, and systems can be added over time. The aircraft becomes a platform, not a finished product. This allows fighter jets to stay relevant as the world changes. The role of the pilot continues to evolve. Future pilots will focus less on managing controls and more on understanding information. They will coordinate multiple systems, aircraft, and missions. Training will emphasize decision-making, awareness, and teamwork. The cockpit becomes a command space rather than just a place to fly from. Despite all the advances, some things remain the same. Human judgment still matters. Clear thinking still matters. Discipline, training, and responsibility remain central. No matter how advanced fighter jets become, they are still tools guided by human intent. From propeller aircraft to jet engines, from speed to stealth, from individual fighters to connected systems. The evolution of fighter jets is not just a story of machines. It is a story of how humans adapt, learn, and rethink their relationship with technology. The future of fighter jets will not be defined by a single aircraft. It will be defined by how well humans and machines work together. As fighter jets continue to evolve, designers are also rethinking where the cockpit fits into the bigger picture. For decades, the pilot and the aircraft were tightly connected. One person, one machine. But future systems are beginning to stretch that connection across distance. A pilot may not always be sitting inside the aircraft they control. In some future concepts, pilots may operate aircraft from secure locations on the ground. In others, a single pilot may guide multiple aircraft at the same time. This does not remove the human role. It expands it. The pilot becomes a coordinator of systems rather than a single point of control. This allows missions to continue longer, reduces physical strain, and opens new possibilities for aircraft design. Future airspace will not be simple. It will be layered with many different systems operating together. Piloted fighters, uncrewed aircraft, support platforms, space-based sensors. Each layer contributes information and capability. Fighter jets will move through this environment as part of a larger structure, not in isolation. Understanding this layered space becomes as important as flying itself. As fighter jets move further into the future, the role of design itself is changing. In the past, design was about shape, strength, and performance. Today, design is also about thinking. Engineers are no longer just shaping metal. They are shaping how information flows, how decisions are supported, how humans interact with machines under pressure. The aircraft is no longer just a vehicle. It is an environment. Future fighter jets may not remain static throughout their service life. They may learn. Through software updates, data analysis, and operational experience, aircraft systems can adapt over time, not by changing their mission, but by improving how they support the pilot. This means lessons learned in one moment can shape performance in the next. The aircraft evolves alongside its operators. One of the most important goals of future fighter design is not to add more systems. It is to hide complexity. The best systems of the future will be the ones pilots barely notice. They will operate quietly in the background, filtering noise and presenting only what truly matters. Success will not be measured by how much technology an aircraft carries, but by how little effort it demands from the human inside. Trust will become a key element of future aviation. Pilots must trust the aircraft. Engineers must trust the systems they create. Commanders must trust the information they receive. This trust is built slowly through reliability, transparency, and experience. An aircraft that behaves predictably earns confidence. One that surprises its pilot does not. The future fighter must be powerful, but also understandable. No matter how advanced technology becomes, The human mind still has limits. Attention can only stretch so far. Decisions still require clarity. Judgment still takes time. Future fighter jets will be designed with this reality in mind. Instead of pushing humans harder, systems will adapt to human limits. This is not weakness, it is wisdom. When future historians look back, they may not remember every aircraft model, but they will recognize the pattern. Each generation of fighter jets reflected the thinking of its time. Early aircraft chased speed. Later ones chased power, then awareness, then stealth, then connection. The future will chase understanding. The story of fighter jets is often told through noise and motion, but its real story is quieter. It is about learning, about balance, about humans trying to understand the sky and their place within it. The aircraft will continue to change. The technology will continue to evolve, but the search for clarity will remain.